Okay, officially we are in module 4 now, integration and applications. Because we already have the fundamental idea about the integration, right? In third module, we learn how to perform integration as the reverse process of differentiation. That's what we have done, right? But here in this unit, we are going to look at some of the techniques of integration. And when you're working on the mastery exercise for unit 3, probably you have learned a couple of techniques already from the videos. Like you have seen U substitution there, right? And the first thing we are going to start here is the U substitution. So U substitution is one of the important techniques of integration. So what we will be doing here is basically in our integrand function, you will have a composite function and also the derivative of the composite function in the given integral. What I mean by that? For example, if you look at this integral here, right? If I want to integrate this one, what you'll see is we have the product of two functions there. We have f of g of x, that composite function is one function, multiplied with the derivative of g of x, and we are integrating that with respect to x. So we have two functions, f of g of x, that is one function, multiplied with the derivative of g of x. But these two functions, if you look at these two functions, what we have is inside the composite function, you have g of x, right? Inside of the composite function is g of x, and the derivative of that g of x is right here. Okay? If the derivative of that inside function is with the given integral, then we can use the U substitution. Otherwise, U substitution will not work. Okay? The derivative of the inside part should be there in the function. If the exact derivative is not there, maybe the multiple should be there. That will also work. Okay? And what we normally do is we try to substitute that inside function. Okay? We'll plug in the inside function as U. So the idea here is, let me write here, we consider that inside function as U. U equal to that inside function, g of x. Then we find the derivative of that function. So we differentiate U with respect to x. So it will be du over dx is equal to derivative of g of x is g prime x. Then if I multiply on both sides by differential dx, we get du equal to g prime x times dx. So this will help us substitute. Okay, this we can use this information to substitute. So if I substitute here, then this integral will be, see, integration of f of g of x. G of x we consider u. Then multiply to g prime x dx. And here you can see g prime x dx is du. Okay, so U substitution, what it will do is, it will change the complex integral involving composite function and the derivative, okay, the product of composite function and the derivative of its inside function, a very complex function, to a very simple integral function. It is just a simple function differentiated with respect to U. Remember, the original integral is in terms of x. Everything that we have here is in terms of x. After you perform the U substitution, everything is in terms of U, integration of f of U du. Okay? While working on your problem later on, after you make the substitution, if you don't see all U, okay, in your integral, then tell yourself that your U substitution is wrong, then go back and start working it again. But remember, the key idea is, in order to perform the U substitution, one more time, in order to perform the U substitution, given integral will be the product. Given integral will be the product of a composite function, like f of g of x. That's a composite function. Product of that with the derivative of the inside function. The derivative of the inside function is g prime x. Do you see that? So it should be the product of a complex, I should say the composite function with the derivative of the inside function. So if you see that, we can perform the U substitution. And U is always equal to your inside function. And by performing the u substitution, we'll be able to change the complex integral to a very simple integral function involving a function of u integrated with respect to u. Okay, so that is the basic idea. So whenever we perform that, we just consider u equal to whatever is the inside function. We do the same math that I have done here on the screen. So let's take an example. So I have two examples here. So let's work on A first. The first one, A. In A, we have integration of 3 times 3x plus 4 raised to 5 integrated with respect to x. If you look at this carefully, what you'll see is this one here, 3x plus 4 raised to 5, that is a composite function, right? That's a composite function. Inside function is 3x plus 4. Outside function is the power function with the power 5, right? We have a composite function, and this composite function is multiplied with 3. Do you see that? And what is that 3? That is the derivative of the inside function, right? So the composite function is multiplied with the derivative of the inside function. So if that is the case, we can use u substitution, right? And u is equal to that inside function. So let's do that. So at the side, we do let u equal to 3x plus 4. Then you differentiate that, du over dx. The derivative is equal to 3. And if you multiply on both sides by dx, it will be 3 dx. Okay, du equal to 3 dx. We got this. We did that little substitution. We want to do that little substitution. So if we perform that substitution, now let's see what we get. This is equal to, okay, this function here, this one, inside the parenthesis, 3x plus 4, that's a u. So that becomes u raised to 5. U raised to 5. And this one, 3 and then dx. 3 times dx. What is that? 3 times dx is a du, right? That's equal to du. So now you can clearly see that this complex integral, which is 3 times 3x plus 4 raised to 5, is simplified to this one. Okay, and it becomes u to the 5. And it's easy to integrate u to the 5 using the power rule, right? Power rule for integration, what we do is we increase the power by 1 and divide by the new power. So that becomes u to the 6 over 6, then plus the constant of integration. That is my answer, but not the final answer, because our question is in terms of x. So my final answer should be in terms of x. So I have to resubstitute the value of u. And you know that your u is 3x plus 4. So we can write this as 3x plus 4 raised to 6 divided by 6 plus c. So that's how we can perform u substitution and solve a problem like this one. Okay, any question on that? No question? It's very easy. Okay, we did the first one. Now we are going to look at the second one. Second one can also be done using u substitution. So I'm solving all the problems in this first portion of the class using u substitution. We can do this one using other method also. It's possible to do by other methods also, but today my focus will be u substitution only, okay? So if you look at B, let's find out. In B, we have integration of 10x minus 2 multiplied with the square root of 5x squared minus 2x with respect to x. So if you look at this question here, this is square root function, square root of 5x squared minus 2x. That is the composite function, right? The outside function is the square root function, And the inside function is the quadratic function 5x squared minus 2x. But if we look at this little carefully, what we will see is the derivative of this inside function is right here. Because derivative of 5x squared is the 10x, and the derivative of negative 2x is minus 2. Do you see that? The derivative of the inside function is also there. So this integral is also the product of composite function and the derivative of that inside function. So if that is the case, we can use the u substitution. And u is always equal to that inside function. U is equal to that value. So let's write it down. Let u equal to 5x squared minus 2x. If you find the derivative, du over dx, that is equal to 10x minus 2. And if you multiply on both sides by dx, it will be 10x minus 2 dx. So du is equal to 10x minus 2 dx. Now we can make that substitution there. So this will be equal to integration of, so first we are going to substitute this one here, this one. That is the square root of, inside that we have 5x squared minus 2x, that's a u. And then 10x minus 2 times dx, that product is equal to du from our substitution. So you can see, when you look at the question, it was a complex problem there, right? A long expression there. But after we perform the u substitution, you can see this is reduced to a very simple problem there. Square root of u is same as u to the half. So I can rewrite that as integration of u to the half with respect to u. And in order to integrate this, you can use the power rule. You increase the power by 1, so that becomes u to the 3/2, and then divide by 3/2 by the new power plus c. That is my answer, but not the final answer, because I cannot leave my answer in terms of u. I must have my answer in terms of x. So here we are dividing by 3/2. Dividing by 3/2 is same as multiplying by 2/3, right? So that can be written as 2/3. 2/3, the value of u is 5x squared minus 2x. Power is 3/2 plus c. Is that easy? Yes? Okay. It's not that difficult. Yes. Why do we, what? You mean u to the front means, okay, so when you make the substitution, right? You mean to say when we make the substitution? Okay, when we write the general integration, we always write dx or du at the end. That's why you have to write the first term without du or dx first. Okay, that's a standard notation. Okay, because like dx goes at the end, du should go at the end. That's why. Okay. Any other question? Just a beautiful question like that one? No? Okay. Okay. Here is the next one. Next two problems, I should say. Use the u substitution to compute the following integrals again. Again, we are using the u substitution. If you look at the first one, carefully, you should see that here you can use the u substitution. We have integration of square root of x plus 2 quantity cubed over 2 root x with respect to x. What we see here is this one. Look at the board. This quantity here, x plus 2 raised to 3. That is the composite function, right? And the derivative of that inside function, outside function is a power function, a cubic function. Inside function is square root of x plus 2. And the derivative of square root of x plus 2, square root of derivative of 2 is 0. Derivative of square root of x is 1 over 2 root x. Do you see that in the denominator? Right? So the derivative is right there. If the derivative is also there in the integral, then you know that you are going to use the u substitution. So let's perform that u substitution. Let u equal to square root of x plus 2. And the derivative will be du over dx is equal to 1 over 2 root x. And then if I multiply on both sides by dx, then it becomes dx over 2 root x. Du is equal to dx over 2 root x. And we can make this substitution over there so that we can change everything from x to u. So this is equal to integration of, let's substitute the numerator. In the numerator, we have square root of x plus 2, that's a u raised to 3. And then what we have here is, after we make that substitution, you have dx in the numerator and then 2 root x in the denominator. So that is dx over 2 root x. And if you look at the little work we did at the side, dx over 2 root x is equal to du. Okay. So the complex integral involving square root in both numerator and denominator and also the power 3 is now simplified to very, very simple integral u cubed. And you know how to integrate that, right? Use the power rule, increase the power by 1 and divide by the new power. So that is u to the 4 over 4 plus c. And the value of u is square root of x plus 2 raised to 4 divided by 4 plus c. That is my final answer. Remember, before this unit, at the end of module 3, we learned the integration using the reverse process of derivative, right? That was one method, reverse process of derivative. In fact, that is the definition as well, right? So we can solve, technically, we can solve any integration problem using the reverse method of derivative. But there are some specific, methods that we need to know so that the integration process will be easy. Like the u substitution here, okay? This is making the integration process very, very simple. It doesn't mean that we cannot do this problem by other methods. We'll be able to do this problem by other methods also, okay? But it may take a little longer time. Or if you think of the problems that you have done at the end of module 3, right? At the end of module 3, we did the integration problem. We did the reverse process of integration only. Probably there were some examples which we could have done using the u substitution. Maybe they will be much easier if we had used u substitution there. Okay. Let's do this one now, B. I think this is the last example on u substitution. So in B, we have integration of 5 times e to the negative 5x dx. This one involves a little bit of work. Because if you look at this function here, e to the negative 5x, that is the composite function, right? Your outside function is the exponential function, and your inside function is not x, but negative 5x. Do you see that? Negative 5x. So your inside function is negative 5x. What is the derivative of negative 5x? Negative 5. We don't have negative 5 there. But we can easily manipulate this and then make that the derivative. If I want to make that negative 5, what I can do is, we can always do a little bit of math there. If I do negative there, I can also put a negative outside. Does that make sense? Because negative and negative, that's a positive, right? And if we write like this, this negative 5 is the derivative of that. And the reason is, in order to perform the u substitution, we must have the derivative of inside function there, right? Then the u substitution will be easy. Otherwise, it will be difficult. That's why I make that negative 5. If I make that negative 5, I'm changing my question. I'm not supposed to change my question. So I'm also multiplying by a negative outside. Negative and negative is positive. I have not changed the question. Okay, just a little bit of manipulation. Now I can write that u substitution. Let u equal to the inside function, which is negative 5x. U equal to negative 5x. So the derivative will be du over dx is equal to negative 5. Derivative of negative 5x is negative 5. And if you multiply on both sides by dx, you'll get du equal to negative 5 dx. This will help us substitute easily and solve that problem. Now we are ready to perform that substitution. So what we do is we make that substitution. So we have that negative sign outside. I'll write that as it is, negative. And then we'll make the substitution here first. Okay, e to the negative 5x. That is e to the negative 5x is u, e to the u. And then negative 5 times dx. That's what is remaining, right? Negative 5 times dx. And negative 5 times dx is a du. So we can write that as du. And what do we get after that? Negative as it is. Integration of e to the u is also e to the u, because derivative of e to the u is e to the u, right? So that is e to the u plus c. That is my answer, but not the final answer, because I cannot leave my answer in terms of u. What I have to do is I have to substitute the value of u, which is negative 5x. So that becomes negative 5 times e to the, not negative 5, sorry about that, negative e to the u is negative 5x, then plus c. We just substitute the value of u. So that is my integral. So remember, in some of the problems involving u substitution, like in this example, you may not see the exact derivative there. Okay, you may not see the exact derivative of that inside function. In that case, you have to do the little bit of manipulation by multiplying or dividing, so that you are not changing the question, but you're just manipulating it so that the derivative of the inside function is also within the integral. Okay, so that will make the u substitution process easy. So this is one of the important methods of performing the integration. And in fact, for calculus 1, this is very important process that you really need to know. Okay, now in chapter 3, one more time, we did the integration as the reverse process of derivative. We are using the derivative formula to find the integration. Here we learned the u substitution. The next one that we are going to look at is still the reverse process of derivative, but we are looking at a special type of functions, that is the trig function. So here we are looking at the indefinite integral of the trigonometric function. We are looking at the indefinite integral involving the trig function. You may look at your note catcher and check, you may have some general formulas there with ax. If that is the case, that's totally fine. Are your formulas similar to this or a little bit different? Little different, because those are the composite function. You may have ax there, right? That's totally fine. If that is the composite function, the formulas will be like that. If we are not using the formulas in the composite form, then the formulas are just like this. You can just look at your note and try to compare. If we want to integrate sine x, it will be negative cosine x plus c, because the derivative of cosine is negative sine x, if you remember, right? Similarly, derivative of cosine will be sine. Derivative of tangent will be natural log of secant x plus c. Okay, derivative of cotangent will be natural log of sine x plus c. Derivative of secant x will be natural log of secant x plus tangent x plus c. And the derivative, I mean, integration, if I'm saying derivative, okay? Integration of cosecant x is negative natural log of cosecant x plus cotangent x plus c. What I'm going to do is, I'll not have time to derive all these formulas, but I am going to pick one in the middle and then show you how we prove that. For example, this one. Let's see how the derivative of tangent x with respect to x is the natural log of secant x plus c. Let's prove this one, at least one, okay? So suppose I want to prove that. Let's see. If I want to prove that, what I have is, I have integration of tangent x with respect to x. I can rewrite it like this. Integration of sine x over cosine x dx. Is it same thing? Tangent x is sine x over cosine x, right? What is the derivative of sine x? Cosine. So look like the derivative of sine is there. So I'm going to use u substitution here if it is going to work. I'm going to consider u as the sine x. Let's do it. Let u equal to sine x. Let u equal to sine x. So the derivative of u with respect to x is equal to derivative of sine x, which is cosine x. Hold on, let's do this instead. Instead of doing u equal to sine x, let me do a little bit differently so that it will be a little more easy. What is the derivative of cosine x? Negative sine x. Let me go that route, okay? Let me use the cosine because substitution will be much easier if we do that. Let me use cosine x. U equal to cosine x. So the derivative du over dx is equal to negative sine x. So you get du equal to negative sine x dx. But in this integral here, we don't have a negative sine x. We just have a sine x, right? So we'll use the same technique we used in the previous example. So we multiply by what? Negative, right? We do negative, negative like that. Then the fun part is this. This will be equal to negative integration of cosine x in the denominator. You know that cosine x is u, and that is in the denominator. So that becomes 1 over u. 1 over u. And then negative sine x dx, which is there in the denominator. Negative sine x times dx, what is that equal to? Du. That is equal to du. Okay. Now you know this integration. Negative as it is. The integration of 1 over u is the natural log x, right? Not natural log u, because the derivative of natural log u is 1 over u. So that is natural log of absolute value of u plus c. I put the absolute value because this quantity here, the argument of the log must be positive, right? So just to make that positive, I'm using the absolute value of u. Now, we are going to play on this little bit. That's my answer, but not complete answer. So we are going to play with that a little bit. So what I am going to do is, I'm going to rewrite it like this. This one, negative in front is same as -1. Is that right? And if I use the exponent rule for log, it will be natural log of u to the -1 plus c. Because in log, the exponent can be coefficient or coefficient can be exponent, right? So that is the law of log. So we can write this as natural log of u to the -1. U to the -1 is the reciprocal of u, right? The reciprocal of u, I can rewrite it like this. That is equal to natural log of reciprocal of u plus c. And we can substitute now. Natural log of absolute value of 1 over cosine x. U is cosine x plus c. Natural log of the absolute value of 1 over cosine. The reciprocal of cosine is secant, right? That is a secant x plus c. So you can see that we use a simple technique of u substitution and we prove this formula. Okay, integration of tangent x is natural log of secant x plus c, right? So u substitution is kind of powerful. It will help us to, find the formulas because we have not learned something like this. We have not learned the derivative of absolute value of secant x, right? We have not done that. If we have done the natural log of secant x derivative, then it's easy for us to integrate backward, but we have not done that. That's why some of the integration formulas are required here. It's not always we'll be able to do that reverse process. We also need to know some of the integration formulas. So these integration formulas, I think first two are kind of obvious from the derivative formulas, but after that, these are a little different, right? So these are the formulas that we need to remember. 3, 4, 5, 6. These are the formulas that you need to remember. Okay. So you can try to derive the remaining at your home. You try U substitution or some other techniques from trigonometry and calculus and try to derive them if possible. Obviously, it's possible, right? Okay, now let's look at the integration of trig functions, right? Integration of trig functions. We are going to use the formulas from the previous slide, plus we have studied the U substitution. We'll also make use of U substitution here. Okay, formulas from the previous slide, plus U substitution. Okay, so the first one. If we look at A here, it's awesome, right? Sine raised to 10 theta, I can write sine theta raised to 10 times cosine theta d theta. Sine power 10, I can write like this, sine theta to the power 10 multiplied to cosine theta d theta. Because if I do that, what I can see is this is the product of composite function and its derivative. Because the composite function here is the power function with power 10, and then the inside function is sine theta, right? And the derivative of sine theta is cosine theta, which is also there in the integral. So U substitution works here. So let's do that U substitution. Let U equal to sine theta. That means du over d theta is equal to cosine theta. We are integrating with respect to theta. So du equal to cosine theta d theta. Du equal to cosine theta d theta. Now we are ready to substitute. So we are going to substitute here and check what we get. So this is equal to integration of, we are going to make this substitution first. That's a u raised to 10. And then this product here, cosine theta d theta, is du. Now you can clearly see the complex integral involving the trig function is reduced to very simple integral, which can be easily integrated using the power rule, right? So we have u to the 10. If we use the power rule, what do? We increase. That's right. We increase the power by 1, and then we divide by the new power. So that will be how much? U to the 11 divided by 11. Very good. U to the 11 over 11, then plus C. That is my answer, but not the final answer. Not the final answer, because I have to write my answer in terms of theta. And here we know the value of u. U is equal to sine theta. So sine theta raised to 11. Sine theta raised to 11 over 11 plus C. We can write like this. Dividing by 11 is same as multiplying by 1 over 11. Then sine theta raised to 11 is sine raised to 11. Then theta, that is how we write the trig function, then plus C. Right? So we get 1 over 11 sine raised to 11 theta plus C as the integral for that function. If you have any question on that, let me know. Yes.
So I say that to be 11 over 11, how is a correct answer, or do we have to take or do we have to write it as,
Oh, you mean if you leave it here, will that be correct? Second last step. If you leave that at the second last step, that will be correct. Yeah, that will be correct. But in trig, we just write in that form. That is a standard form. Okay. I still want you to write in the last form, but I'm not going to reduce any points if you leave it there. You'll not be losing points by writing that in that format. So you have seen that in the first example, A here. We use the U substitution. It involves the trig function also, right? Trig function, but we are using the U substitution. Now, if you look at this one, B, in B, it is the mix of the algebraic function and trig function. Let's see whether we'll be able to use U substitution to solve this one. So in B for beautiful, we have integration of 3x to the 4 sine x to the 5 dx. Now you have to look at this carefully. We have the product, definitely, right? Sine x raised to 5, that is the composite function. Outside function is sine, and inside function is x to the 5. That is the composite function. If you look at the derivative of the inside function, what is the derivative of x to the 5? 5x to the 4. Do you have 5x to the 4 here? We only have 3x to the 4. That means I have to do a little bit of math and make it 5x to the 4. Okay, so this is how we can do it. Let's play something. So let me pull that 3 out. If I pull that 3 out, it will be x to the 4 sine x to the 5 dx. By pulling that 3 out, I have not changed anything. Oh, it didn't show up there. That is the problem. Okay, so just give me 1 second because I need to reshare this. Do you see me on the screen? Yeah, that's me. That's me teaching somewhere. Okay, let me try to share it again. Okay. Do you see it now? So I factor that 3 out there. That's what I'm saying. So by factoring that 3 out, the value has not changed, right? Value of the integral has not changed. I just factor that 3 out. But what I was looking for is the derivative of x to the 5. What is the derivative of x to the 5 again? 5x to the 4. Here I want 5x to the 4. So what I'm going to do is I am going to multiply there by 5 and also divide by 5. And again, it's not showing, right? I don't know what's going on. Interesting. This is kind of interesting. It's there, it's here, it is there, but it's not there. Let me say it one more time. Is it the problem with the projector? Right, right. Yeah, because I'm sending through projector, so. I'm like common projector, right? Okay. That's what I did, but let me see if it is actually showing it. It's not showing it. Okay, interesting. It's not break time yet, right? And they're like, go for break.